Hello, my name is Wally Boot, and welcome to the first webinar in the Enhance webinar series. Enhance is a Rehabilitation Engineering Research Center, or RERC, funded by the National Institute on Disability, Independent Living, and Rehabilitation Research, with a focus on developing novel technology solutions to help older adults living with a cognitive impairment live independently. This webinar is produced in collaboration with the Rehabilitation Engineering Research Center on Accessible Public Transportation, or RERC APT. Today, we're lucky to have the co-director of RERC APT here, Dr. Aaron Steinfeld. Dr. Steinfeld is an associate research professor in the Robotics Institute at Carnegie Mellon University. His educational background includes degrees from the University of Michigan and a postdoc at UC Berkeley. He leads multiple multidisciplinary research centers and teams on accessible transportation, inclusive web technologies, and human-robot interactions. We are excited today for him to share his expertise related to the exciting and fast-moving topic of artificial intelligence in accessibility and rehabilitation. Welcome, Dr. Steinfeld, and thank you to everyone for joining us today. We hope to have questions and time for questions and answers at the end of today's session. We ask that you use the Q&A feature at the bottom of your screen, and co-directors of the Enhance Center, myself and Dr. Sarah Saja, will moderate the discussion. I'll now turn it over to Dr. Aaron Steinfeld. Thank you.
Hello, everybody. Just as a quick housekeeping thing, I try to keep the upper right corner generally clear. So for those of you who are going into full screen mode, if that's where you're going to put my video box, that should work out pretty well for most of you. Okay, so one of the things I want to highlight is I've gotten in the habit of when I give my name on talk slides and whatnot, I have a habit of putting in et al. And a big reason for this is that our lab is incredibly collaborative. Almost nothing we do is done by a single person, and this is a hallmark of robotics and AI. You know, the Tony Stark solo inventor is a real myth when it comes to computer science and robotics, and I feel it's really important to stress that. And so in keeping with that, sorry, I'm not in the correct app. In keeping with that, we have a pretty large collection of people who work on our group. The people who work in our team is a mix of computer scientists, engineers, people with psychology backgrounds, design backgrounds, a whole range of different capabilities and skills. I do work with a lot of other faculty here at Carnegie Mellon, too many to list, and I also work with many collaborators at other institutions and stakeholder groups. In particular, the RERC APT is our partners are University of Buffalo, the Idea Center. There's another project. There's two other projects that are center projects that include partners at UMass Lowell, BYU, Tufts, and another group is with another project has University of Washington researchers there. I'm also going to kind of mention some work that has some alumni activity in it, and I do want to highlight specifically Chen Yang, who is a first-year faculty up at Cornell in Ithaca. She's done a lot of work on how do you do interaction design for AI systems, and you'll see some of her work in this material. A big chunk of her research was funded out of the RERC as a result of us learning and discovering what we didn't know about how people interact with AI systems and how to design for AI systems. So her work was kind of partially funded from the RERC. So I'm going to be skipping across a bunch of different projects, but one of kind of the and examples and lessons, but one of the key things I want to stress is that universal design, which I'm assuming many of you have heard about, and is kind of a key strategy for making things accessible, is really compatible with AI. For those of you who don't know and may have guessed by my last name, my father is Ed Steinfeld, who is involved in both the UD principles and the goals of universal design. And he and I, for years, have had conversations about how AI, machine learning, these sorts of things are actually have a real potential to have a very powerful universal design effect, because AI and machine learning are particularly good at adapting to the user. And so you can see a lot of personalization, you can see a lot of flexibility, and so you might have a system that starts out as kind of being generic for everybody, but it learns how to interact with a person with a disability, or it learns what they need to dramatically cut down on the effort needed to work on a task. And so this idea is really important, but the caveat is, of course, it needs to be applied correctly. I'll get to it later, but there are lots of issues with equity, and there are some issues with errors in AI and machine learning systems. And so it's important to keep these in mind when working on them. So one of the lessons that the field of computer science should have learned by now, and many of us have learned, but many have not, is that before you do anything about bringing AI or machine learning into a system, you should first figure out what is the problem that the user has, what is the context in which they're using the technology, and where are your opportunities to make an impact with the technology. And so one of the things we do on a regular basis is to really work with stakeholders to identify the entry points for the technology, and the societal and other factors that influence how a technology might be used. We do not start with, this is the AI technology we want to use. Instead, we start with, this is the problem we want to solve, and then we try and figure out what's the AI technology to bring to the table. A hallmark, unfortunately, of computer science and robotics research is people who are very good at a particular technology go shopping for a way to use that technology. You can do that, but you have to be super careful and work very hard to make sure you find the right problems to bring that in. Otherwise, you end up with a real misfit of technology to use. The example I like to give in this is a lot of people who make mobile robot systems think that they can make a smart cane for people who are blind, and you end up seeing these like robots with wheels with a cane attached to it. And if you really kind of learn something about how white canes are used and why they are so effective, you'll very quickly understand why this is generally not the right strategy. There are better ways of trying to help people who are blind navigate through space, and I'll be coming back to that later. An example of how you can kind of do another example of a design principle is to think about what Chen labeled unremarkable AI. A lot of people come up with these AI systems, and they really kind of interrupt the user's workflow, and they ask the user to do all sorts of extra steps or break their existing workflow to get benefit from the AI system. And time again, this is shown to be a problem, and we see this a lot in decision support systems decision support tools for doctors in particular, where they're asked to enter in all this data, and then they get recommendations on what to do from a clinical perspective. And this is generally, they get all these great results in controlled laboratory experiments or in simulated experiences with medical students. But when they get out into the real world, these things tend to fail rather miserably. And a big reason for that is because they're not integrated into the workflow. The example here is a design concept that Chen developed and then vetted with a variety of ventricular assist device clinics to figure out if this is the right kind of approach for introducing predictions into their system. And so in this example, one of the things that happens with ventricular assist devices, these are artificial hearts, is that the decision on whether or not to implant occurs not by an individual doctor, but typically by a team during a presentation and a discussion session. And they factor in an enormous number of different metrics into these decisions, some of which have to do with family support, some have to do with actual medical measurements. And this is typically a multidisciplinary team of nurses, doctors, social workers, and whatnot making this decision. And by embedding this into the slide that is shown during the meeting, they're not, the idea is that you're not breaking their workflow of that decision, and you're providing the context and an opportunity to discuss this, but that's as a piece of one of the many different sets of information that get used. And so if you're thinking about things like decision support tools, you really need to pay attention to workflow, and there's other examples where workflow is super important in terms of how AI is introduced. This shows up in robotics too. The other thing I want to emphasize is that the way that a person interacts with AI systems is influenced by the performance of the AI system. And so one of the things, for example, is when you're looking for an item out of a list, certain kinds of AI systems can kind of predict what you're going to pick out of that list. And how you design that experience should be influenced by how good the AI system is at pulling out what you want. And so you have to think about, okay, well, what if the suggestion is wrong? Or at what threshold do I need to kind of not provide a suggestion? And these are the sorts of decisions you need to make when bringing an AI system into a user experience. And unfortunately, a lot of developers don't think this way. They just put it out there. So they'll jump straight to element D, where they just give you the predicted item, and they make it either confusing or difficult to find the correction to the recommendation. And so we've learned this the hard way over the years in a number of different systems, and this is one example of a design interaction that's really important. There's a bunch of other examples in Chen's paper in 2016 on wireframes for AI design. But this is a mistake that a lot of people make, and it's really important to think about this up front. Now, these are the user interaction issues, but then you kind of also have to get into what is the AI system that you're going to use to have this experience occur. And traditionally, and I'm being very abstract here, like a hardcore AI person would probably be spitting their coffee out right now. But at an abstract level for non-experts, AI tends to come in two different flavors, symbolic and statistical. And some of the terms that you may have heard or seen in the popular press kind of generally fall into one of these two camps. The old school traditional AI approaches are typically symbolic in nature. These are like expert systems or case-based reasoning. Many of the decision support tools are based off of these types of structures. But recently, machine learning approaches that are more statistical in nature have become very popular. This has been driven heavily by Google's success in the search field. And basically what happens here is you build up kind of a history of what has happened in the past, and you learn by looking at these examples and the training data. And some of the statistical approaches can be extremely powerful and very, very good, but they do have some weaknesses. And so what you often see in commercial systems is a mix of the two, where you're trying to get the best of both worlds. For example, a statistical approach technique for a computer vision system will be able to identify a human in the world, but it may not have the ability to reason carefully about what is going on with that human or really understand what's happening. And so a symbolic approach might pull the knowledge that it is a human and then start doing some reasoning about what's the human actually, the more other characteristics about the human and what they're doing. We see this also heavily in speech systems where there's a mix of the two. So we in my lab and my colleagues, we tend to do a mix, but I'll give you some examples to make this a little more concrete. So when you talk to Siri or a conversational agent, quite often what's happening is the speech is being converted into text. That text is then being parsed into explicit entities. So for example, your location, your XY coordinate space in the world, the name of certain points of interest, that's an example of a kind of a symbolic representation. Times, also another example of symbolic representations. And stops, bus stops. You know, there's an explicit bus stop at this location that has a representation. It's not just some kind of learned object. Sometimes these entities are hand-coded in or brought in from existing data systems. So, for example, in this case, many transit systems now have data files that can characterize the entire transit system in a very symbolic manner. There's something called GTFS, which is the data structure that almost everybody uses nowadays. And in that, every bus and every stop and every route is articulated in this data file. And so you can kind of try and, you know, do reasoning on those objects using traditional symbolic techniques. And you can kind of run queries against these databases to find the objects that you're looking for. And so we've been, so we do public transportation, and so we've been very interested in recent years on conversational agents for accessing transportation information. So for example, you know, if I give you a printed schedule of a transit route, a sighted person, for example, can kind of work the table, and, you know, if they're experienced with the table reading, they might be able to find the right information about their bus. A more universal design approach would be to allow a person to just query and say, you know, when's my next bus, either by texting into a chat bot or speaking it into a system, and then have the AI system kind of pull the information out of that table directly. We had done some work under non-transportation research on screen readers and tables, and it's very hard for a person who's blind to kind of work their way through a table. And so the aha moment was, well, what if we give them the ability to query the table and ask a question and have the system come back with an answer? This turned out to be incredibly successful for people who are interacting with web tables. And from that, we're now moving into more mobile experiences in the transit space. An example of a statistical approach from our work is what's going on with tiramisu. We're on version 3 right now. Version 1 and 2 was exploring a different research question, more about crowdsourcing and things like that. Version 3 is really focused on statistical learning and personalized experiences. In many city environments, when you pull up one of these transit apps, you get a list of like 20, 30 options of what you could take based on where you're physically located. Obviously in New York City and Manhattan, it's a much higher number. But this is an example from Pittsburgh where at this particular location, there's about 14 different rows that would appear in this interface. And if you use a screen reader, or if you have a cognitive disability, or if you're just in a hurry, this can be really problematic. You can pull the wrong direction, you can get the wrong bus, and so our system allows users to go in and select things to filter. So for example, the manual filtering is with blue. So in this case, the user has clicked 61C because they want to see data from the 61C. Well, so what we did is we watched how people picked the filters based on where they were and what time of day and which day of the week. And for each user, we built up a personalized model of the filters we thought they would select at a given time. And in the orange, you see the system is pre-filtering by automatically selecting it for them. Now, I want to go back to this point about error correction, right? So say it picked in, and that was not the right answer. For a user, all they need to do is just tap the in button, and the filter goes away, and that machine learning error has been corrected, and the user has recovered from that error. We've made it very easy for people to tell the system they're wrong, or to tell the system it missed something, like the 61C in this case. And we did this as a large A/B study where we randomly assigned people into either having the pre-filtering or not having the pre-filtering running, so adaptive or non-adaptive. And we also logged who was using a screen reader because we specifically wanted to see how this affected people who are blind and low vision. And we had 41 people who were blind, low vision, who used the screen reader, who got the adaptive experience. And we compared them to the 150 people who just randomly didn't get it. This is kind of a random assignment. We assigned people before we knew whether or not they were using the screen reader, which is why this is not perfectly balanced. And what we found is that, over the course of 2,600 sessions, times of people using the app, we saw that this was particularly effective at reducing the user interaction effort, giving them the ability to get their information faster. We log everything in the app. We also did an analysis of how error influenced this. And this work was just published last year. So I'll give you now some other examples. So I mentioned that we're looking at conversational interactions with transit information, and there is this really hot technology called GPT-2 and GPT-3. If you want to see some really amazing stuff, go look at some of the examples for GPT-3. There's some videos out there of people interacting with it and so forth. These are really amazing systems in terms of their ability to manipulate language, recognize language, and express language. So for example, in the white paper in GPT-3, they give some examples of the system generating text, and then they check to see how well people could detect if it was automatically generated or not. And I got to tell you, it's really scary how good this is. But at the same time, it also fails miserably in certain cases. So it's kind of fragile in that regard. But it's really impressive where these things are going. The way these two systems work is massive, massive, massive data sets. And they do this by just learning patterns and kind of, what have people done? Which words go together? Which words don't go together? So there's really almost no understanding. It's all imitation, basically. And so if you teach it math, so 1 + 1, if it's seen examples of 1 + 1 in its data set, it will know how to do 1 + 1. But that doesn't mean it knows how to do math. It doesn't understand the concept of addition or subtraction. Instead, what it's learning is just the associations with those things. So complex math questions fail. So for example, if, asking when you have to leave to catch a bus, or if you're going to make your connection, these sorts of complicated, they're not actually that complex. If from a math perspective, you and I can do these relatively straightforward, but the system fails on these. And so we're looking at mixing GPT-2 in particular with some more traditional symbolic approaches to try and address some of these types of questions. Access to GPT-3 is still somewhat controlled, but GPT-2 is a lot easier to get access to for researchers. Okay, I'm going to give you some other examples. As mentioned, I do work with robots, and people love robots, and so I'm going to give you some examples here. I also collaborated a lot with the Cognitive Assistance Laboratory. This is Chris Katani, Jeff Bigham, Chieko Asakawa from IBM. I want to give you some examples of cool things you can do with AI when you start applying them out into the world. So I mentioned smart canes as being kind of a common thing that kind of keeps coming back. One of the things that, the big challenge is, of course, nobody wants to carry around extra gear, but if they do, they want it to be something that they're going to bring with them anyway. And so your phone is something that a lot of people carry with them all the time. And so Chieko and the others have been looking closely at using smartphones and AI technologies and other localization technologies to do things like path planning and computer vision to really generate some powerful experiences. Chieko has a TED Talk that's really kind of cool to watch with some of the concepts and applications in use. And so the way that this team has solved some of the localization problems for smartphones, because many of you have probably carried your smartphone into buildings and seen that the localization is not that great, is they've placed low energy Bluetooth beacons all over various buildings, and then with that they can do triangulation based on a learned model of the space. They can then assign you to a specific point in the map, and from that do all sorts of interesting navigation and routing approaches. So, you know, you might be able to get pretty good performance with Wi-Fi and GPS, but if you want to get the person on the correct side of a hallway or right up to a specific door, you need better accuracy, and so that's where the Bluetooth beacons come in. This is a picture from the Pittsburgh airport. There's beacons throughout that entire space. We also have beacons all over several buildings at Carnegie Mellon, and Sheiko splits her time between Japan and Pittsburgh, and they have done this also in a large shopping building. And so from this, you can do some really interesting things, like bring a person right to a specific door. But you can also do things with the cameras. And so if you put your phone in your pocket a certain way or wear a wearable camera, you can use people detectors to identify that you're approaching a person. You can use emotion recognition to see that a person is smiling. You can do all sorts of really fascinating things just by kind of building off of the fact that these cameras exist. Now, the other question Sheiko and the others in the team had was, well, okay, if you're traveling in an airport, you have a suitcase often. What if you outfitted the person's suitcase with some of these technologies and took advantage of the fact that you have a little more space than a phone? So the picture you see here is a suitcase that's equipped with collision avoidance detection, collision avoidance and people detection capability, and so it's actually alerting people that they're about to be running into they're in the way, or alerting the user that they're about to hit someone. I'll come back to privacy later. I see the question. Okay, the other example I want to give you is a project that one of my grad students was working on. When you work in robotics, you pay attention to the robot toys because, like, let's face it, they're cool. And there is a particular toy out there called the Sphero, and they have a version that allows people to hack and develop on it. And this is a picture of a person holding that. And one of the nice things about this particular piece of technology is they're really, really tough. You can drop this from, you know, your shoulder height, and it won't damage it. It's been optimized for battery consumption. It already has Bluetooth and, you know, kind of communication with your phone. It's got all sorts of stuff solved for us already. And they sell this thing for, you know, in the vicinity of $100, which in the world of assistive technology is cheap. And furthermore, you can buy it from Amazon and drop ship it, you know, relatively quickly overnight if you need to, and just pair it to your phone if something goes horribly, horribly wrong. And so we were thinking, could we use this as a haptic guidance system? So normally this is just like a hamster wheel robot that drives around on your floor. But if you pick it up and hold it, we can generate all sorts of interesting haptic signals. And could you use this to provide guidance to a person? There have been other attempts to make haptic signal systems for people who are blind, but they use custom equipment, you know, and that means expensive cost. What we found is that we could, again, using some machine learning techniques, develop some really interesting ways of expressing direction. And so the idea being is that if you were blind, for example, you could have this in your purse or your, you know, or your messenger bag, and you could tuck your hand into the bag and hold on to this and get the signal from it and surreptitiously be getting guidance without kind of advertising the fact that you're blind. It works okay. It turns out that we need certain modifications to the hardware to really make this work better. But theoretically, it is possible to do something like this. People have also been exploring different ways of providing vibration through the phone or through watches. If you've ever tried pedestrian guidance using Google Maps, and you close your phone and you enable vibration, there's a thing where it will vibrate like twice for turning in one direction and 2 or 3 times, I think 3 times for turning in the other direction, and things like that. Also, smartwatches have made it a lot easier to provide kind of surreptitious directions and guidance. And of course, Bluetooth headphones have made this a lot easier too. But these are examples of how you might kind of leverage low cost, or at least reasonably cost, commercial systems to kind of provide additional help through the application of AI and machine learning. Now, the other thing that comes up is, well, okay, what if we put a robot in the building, and instead of you having to own the equipment, the building owns the equipment and it helps you when you get there. So this is already happening in some airports. So here's an example from Incheon Airport near Seoul, Korea. They have a number of robots wandering around helping people. This is a deployment done by LG. And there's several other places that are starting to do this too, but these are generally more designed around, customer service and kind of providing an attraction for people. When these types of robots are running, you almost always see kids walking around them, checking them out. But you could theoretically do some really fascinating things with these for people with disabilities. So one of our projects looks at this. In fact, two of our we had an older project and now a current project to look at this. We've been looking at kiosk robots that give directions. And we've been looking at mobile robots that meet people, much like this robot in Incheon, and take them places. So one of the things that comes up, this is BC Min, he's faculty at Purdue now, he's one of our postdocs. When we realize is people who are blind, especially people who have been blind from a very young age, there's no preconceived notions about robots because they don't see robots. And they don't see like this is a big red robot. They just know that there's a robot there. They can kind of hear the motor, so like standby mode, but that's about it. So we even had to look at how does a robot introduce itself to a person so that a person who's blind understands what the robot is and what it can do. You or I can look at a robot and very quickly say, oh, there's a hand, it can pick things up, or it has wheels, it can drive places. But if you can't see those cues, you need to be thinking about how does that initiation of interaction occur. And we've also looked at the robots doing things like, so if I give you directions, I might point to places like go down this hall, turn right. And that redundant physical cue is really effective and valuable at reinforcing your memory as to a particular direction. So one of the projects that we did, for example, is we had this is in the upper right hand, the red corner, the red robot is a Baxter robot. It's human safe. It's totally safe to touch because it has no pinch points. Unfortunately, it's not made anymore. But we looked at having the Baxter provide guidance in a haptic and tactile form, so to people who are blind. So, for example, a person who's blind and interacting with an O&M expert, the O&M expert will often draw on their hand to give them a tactile feeling of a map as they describe the map. So that, and there's certain kind of gestures and motions that the O&M expert will do to reinforce certain parts of this memorization. And so we tried to replicate those in the robot, and we found that there are some ways that you can do that do seem to work. But I think one of the problems we kept running into is that robots are so novel that the novelty was kind of washing out some of the power of these approaches. But we think down the road, when robots become more common, this sort of haptic redundancy of information giving will be a powerful way for kiosk robots to help people who are blind. The robot below that is a mobile robot. The nickname for this is Pody, and Pody does, the idea being, what if the Incheon robot had a handle and could kind of escort a person who's blind somewhere? This raises all sorts of interesting, complicated UI questions, user interaction questions, like, okay, I've brought a person to a door. How do I make it so that they can just take their hand off the handle and they are immediately in the right spot to just reach over and touch the door? And if you think about it, there's like 4 different ways that you can approach a door and use this handle to get a person in the right spot. And so we had to do research on that. What's the right one, based on the usability studies. The other thing that comes up, if you've ever guided someone who's blind, they will often hold your elbow and you'll walk down a hall and take them places. Now, if you're not an experienced person, bad things can happen. So my wife is deaf, she's not blind, but and she lip reads. And so very early on when we were dating, we were walking down the hall and she's lip reading me, and all of a sudden she disappeared. And that was because she had walked into a door frame because she was looking at me and not the door frame. And she was assuming that I was looking out for her. And of course I failed miserably at this. And so robots are not that much better than this. When a robot plans a path, most of the robot technologies, they plan the path based on the robot safely traversing that route. They're not thinking about what is happening if a person is holding on to the robot and standing slightly off to the left. And so we had to come up with an entire, new path planning techniques to think about, to kind of be sure that we knew where the person was and guide not just the robot, but also guide the robot in a way that was safe about where the person is operating. So, we had a couple undergrads work on this initially. We now have a PhD student trying to really dial in the safety on this, because this is the kind of thing you really don't want to make a mistake. There's actually a viral video going around right now of a blind mother walking with their child along a train platform, and the mom accidentally brings the kid too close to the edge of the platform, and the kid falls off the platform. Thankfully, everything worked out. Everything's, the kid survived and everything. But that's an example of where a guide that is not aware of their of the relative position of the person they're guiding plus the surroundings can be really dangerous. And the last thing we want are robots walking people into door frames or corners or things like that. And so this is a kind of a really kind of key focus that we're spending some time on right now. Okay. The other subtlety that we've learned over the years, and this is not so much funded by the disability work, but more funded by National Science Foundation and some industry groups, is if you have a robot like this that's going to bring someone somewhere and it just plows through a crowd, you're going to have a lot of problems from a social perspective. And people who can see and can see that that's happening, that's a big problem too. So for example, if you're guiding a person with a cognitive disability through a crowded station, you don't want to just be plowing through crowds, because the person with a disability might be like, oh, I don't want to be associated with this really rude robot, and they might abandon the robot, right? So some of our work in the National Science Foundation work on kind of just general social navigation, we're trying to bring over to these types of systems as well. I see Neil has a question. Okay, I'll come back to smartphones later because that's related to one of my other slides. Okay, so this is an area that we're spending time on. Sorry, I need to switch back. Okay, so the other question we get asked a lot about is autonomous vehicles, because there is, I actually came into robotics from autonomous vehicles, not the other way around. Most people in the world of autonomous vehicles got into it because they were roboticists. And I spent 3 years out of Berkeley, California, UC Berkeley, doing advanced transportation work and autonomous vehicle work. And I remember when I arrived, I told Steve Schladover, who was the person running PATH at the time, and this is right after the 1997 highway demo, if we can make these systems work for people who are blind, you will completely change their ability to get places and their independence. And at the time, everybody was like, oh no, it's too early to talk about this. And I kept asking people and telling people this over and over and over again. And while I cannot explicitly claim credit for Chris Urmson and the Google team taking Steve Mahan out for a drive to get his dry cleaning and tacos, I can tell you that I did have this conversation with Chris before that. And so there's been more and more research showing that this is a population group that really needs to get access to autonomous vehicles. This includes also older adults and people with other disabilities which prevent them from driving, especially in more rural environments. Now, the complicated thing here is there's some really complex cost model and service model questions that need to be resolved. I can get into these if you're really curious. But from an AI and machine learning perspective, there are some very specific and subtle things that are very important that have not been fully addressed. So for example, the computer vision technologies that work on these systems that look for pedestrians, they're not great at detecting people using wheelchairs, because the data that they were trained up on doesn't include a lot of examples of people in wheelchairs. So that's an example of an AI challenge right now. Another one is the interaction with these systems. There's a lot of good knowledge out there about making vehicles accessible and making IT, information technology, accessible, but this needs to be kind of tuned for the autonomous vehicle community. My co-director, Jordana Meisel, and her colleagues up at University of Buffalo, are working very heavily on this area, especially the physical access to vehicles. And we've been focusing on the physical access issues because once you build these vehicles, they're then used, they can be used for as much as 5 to 10 years. Some buses, for example, are used for more than 10 years. And so we want to make sure that those problems are addressed right away, and many of the software issues can be addressed through software updates down the road. So if you're really interested in accessible autonomous vehicles, Jordana can really go into great depth on that. Okay, so one last thing I want to talk about from research results perspective. This comes from our robotics work, but there are direct translations on how this interacts with rehabilitation in older adults. And this is mostly research that's funded by National Science Foundation and the Office of Naval Research. But the performance and capability of these systems is going to heavily drive human trust in these systems. And you need to really pay very close attention to these issues, because if you don't, people will use these robots or these AI systems incorrectly. There's another subtlety that starts showing up in the experience. One of our projects looks at AI systems that can jump from system to system. So if your Siri would jump from your phone into the robot, or from your phone into your home, or you go to a hotel and there's a robot there greeting you. There's probably an AI that's run by the hotel, but there's also an AI that's running on your phone, and there's all sorts of interaction issues that show up here, and a lot of disclosure issues. We've done some studies looking at things like hotel experiences and retail experiences, and in particular, disclosure and privacy of data really show up a lot as kind of unexpected things. And for people with disabilities and older adults, disclosure of information is actually a really high level of importance. And this brings me to my last slide on the downsides. And this gets back to some of the questions that were asked before. So one of the hallmarks of AI systems, and you're seeing this a lot right now, is kind of inherent problems baked into the system as a result of the training data that is used. So I mentioned wheelchairs not being recognized. There are some very famous examples of AI systems learning that people who are of color are more likely to commit crimes because the underlying data is inherently racist. There's also issues with things like computer vision systems not being able to detect people who are black because, again, the underlying data was biased in terms of the data that was fed into the machine learning system. And there's also some decisions made by designers of these systems that can cause problems in this space as well. We're going to see this for people with disabilities as well, because they're generally going to be underrepresented in the training data, and the developers quite often won't even be thinking about them, and so we'll have some problems in this area. The other thing that happens when you apply these things is that the people who use these systems will allow these biases to propagate, because they will just assume that the system is high performing. And the system said it's okay, so I'm going to go with it because it knows better than I do. And the system is making an error, and that's where you run into problems. The other one that comes up is when I talked about the GPT systems being very good because they're building incredible correlations and associations, but they don't have any understanding. And so there's this issue of correlation versus causation. The kind of classic science problem that's out there. This is going to propagate more with AI systems. Then again, there's the social impacts issues. Neil mentioned this issue about smartphones and underutilization. This leads to information segmentation. Some people will have access to these systems and some people won't. I can say there's some promising results on smartphones, is that it's increasingly becoming more and more common. Part of this is that it's harder to buy a dumb phone, but also the other thing that has shown up in some of the research, I think the Pew research has shown that people who are at fixed incomes or lower incomes are using their smartphones as their home computer, and instead of having a home computer, they're just doing everything through the smartphone. So I think that some of the smartphone barriers are going to start kind of eroding, but we will see this in other countries. So one of my students has done some research in Uganda and Rwanda, and one of the things that she highlights all the time is that you know, you and I are very used to kind of always on data, but in some other countries you're kind of paying for data piecemeal, and you might decide not to have data on a particular day because of the cost. Or data might go down in your country for a day or something like that. And so there'll be segmentation based on how data and internet services are provided. And so that may restrict who gets access to which types of systems. And then, of course, if you talk to people in certain parts of the disability community, there is serious concerns about skill loss. You know, people not learning Braille, or people not learning how to navigate with a white cane because they're relying on their phones. And then, of course, there's always issues with, you know, internet addiction and technology addiction issues. And then finally, I do want to come back to the point that I said in the prior slide, which is humans are very bad at accurately assessing the performance of these systems. And these systems themselves are often very bad at doing self-assessment. And these can really kind of lead to some really dangerous mixes where you're putting too much trust and too much faith in a system. And thankfully, there's a major research and major efforts underway within the community to try and really drill down into this and make some of these issues be more manageable and more practical. And so, for example, there are companies out there that just all they do is work on how do you kind of improve these computer vision systems so that they're very good, and how do you kind of identify all the failure modes and problems that occur with them. And we, of course, are doing our own research in this space as well. Okay, I'm going to put up the slides, sorry, the acknowledgements, but then I'm going to address the two questions that I see here. So the Bluetooth beacons, actually Bluetooth is incredibly good at privacy. We actually tried to hack Bluetooth, and me and a student a while back, to use it to generate a particular tracking capability so that robots could meet people at the right location. And we kept failing. It's really, really hard to break privacy issues with Bluetooth beacons themselves. Now, that is assuming that the app that is using it is not kind of sucking up the data for illicit purposes. If you give access to certain companies, they will build profiles and track you. But that comes down to is the system providing appropriate warnings about user tracking and so forth. Google and Apple have become increasingly aggressive about trying to surface these sorts of data disclosure details to users. And I think we'll increasingly see more headway on this, especially because Europe has become incredibly focused on issues of privacy lately in technology. Okay, Neil's question, I talked about smartphone use. Some of these systems, by the way, also work through dumb phones. So our colleagues, Maxine Eskenazi and Alan Black, had a system called Let's Go a number of years ago here in Pittsburgh, where they were doing bleeding edge conversational interaction through a phone line to get transit information. So you could call up just on a regular phone line and get all sorts of transit information by just talking with the system in a natural way. And so there are still ways of kind of going through more kind of low-cost approaches. Yeah, so the plexiglass on station platforms, this is why a lot of platforms now do have these physical barriers. The example that I gave was not from the United States. I think I could not actually hear the language that was being spoken, but when I look at the video, I'm pretty sure it's not in the US, and I'm pretty sure it's not in Europe. So it's probably in a place that doesn't have as much infrastructure investment. Partner with system owners, cities, right. So one of the things that we're thinking about with respect to the robots that live in transit spaces, in transit hubs, transportation hubs, it can be airports, it can be transit, is in many cases these buildings have, there's motivation to put technology into these buildings from a cost perspective. So for example, you may not be able to staff that station 24/7 with a human, but a robot and staffing it with a robot to cover the off hours or to provide service to more than one person at a time could be particularly attractive for a lot of these organizations. Typically at a lot of transit stations, subway stations, there may only be one employee. And they may have to deal with something that's time critical that has to do with, a maintenance issue or whatever. And so if you have a person with a disability, they're out of luck. Or worse, if they're at a different door, they might be waiting, 10, 15 minutes for someone to come. But if the robot, if you're using a navigation app and you say, I'm going to be coming to the station, and it knows where you are because it's tracking you as you walk down the street, and the robot knows to meet you at that door and be there by this time, you can kind of relieve some of these delays that occur because in customer service. Especially in stations that are understaffed. I mean, let's face it, generally transit and transit staffing is generally low compared to what it should be for the level of service that people need nowadays. In fact, when people ask me, how do you make public transit more accessible to people with disabilities, my first answer is have more public transit. It's not the technology, it's just have more of it. And those of you who live in Manhattan know this, right? You're experienced every day what it means to have more public transit. But you can imagine what happens if you only have a service line out once every hour or something, which is quite common in a lot of other cities. Okay, I want to finish up and give time for more questions than the 3 that are here.
Okay, so Aaron, I received a question by email. First of all,
Okay.
Thank you for such a wonderful talk. That was a really great overview of the potential of AI. The question I received by email related to whether or not you're aware of any AI applications that are specifically targeted to helping people with cognitive impairments, such as mild cognitive impairment or dementia.
Yeah. So in fact, I kind of glossed over this, but our project with looking at adaptive user interfaces to kind of reduce the complexity of an app experience, like a transit app experience, we actually, this is really frustrating. We had to, because of COVID, we had to completely change our IRB and our structure, but we were getting very close to running a user study with people with mild cognitive disabilities to see how these adaptive interfaces benefited them and where the weaknesses were. There's also been a number of studies funded by NIDLR. In fact, actually funded back when they were called NIDR. There were actually some projects looking at that as well. So there have been people looking at that. One of the other thing that was done many years ago under the Quality of Life Technology Center, Sarah remembers this, there was a student, for example, who was looking at using machine learning to recognize activity in a person's home to identify whether or not a person was as active or taking their medicines and things like that. He was also doing things like building up a memory record of the person so that they could be walked through these memory records with caregivers to try and kind of help them retain some of their memories. So there has been some work on some very specifically designed systems. I think there can always be more, and I think there always should be more. Given how easy it is now to start introducing some of these technologies, because from a software perspective, it's becoming easier and easier to bundle them into existing technologies. And so I think we'll see more and more of this.
Okay, great. So I think we have time maybe for one last question. Anyone has any questions?
I have a question, Aaron,
Okay.
and thanks. The talk was terrific. Can you, on your second to last slide, there was under the human trust and autonomy, you had the word inertia. Can you expand on that for me, what that is?
Yeah, so there's a thing about human trust. This is across anything, humans and technology, is that we tend to have an inertia. So if we're distrustful in the beginning, we tend to stay distrustful, or if we're very trustful, we tend to be, we tend to not lose that right away. So that people's changes in trust are not instantaneous. So if you're over trusting a robot, you might continue to overtrust it until you learn otherwise. It might take more than one experience. But likewise, the bigger one is that people tend to be distrustful of these technologies, and so it might take them a little bit of time before they really kind of accept the benefit that it can provide to them. But if it's a good system and it works well, people will the influence of the inertia will drop. Yeah.
Okay, great.
So,
oh, sorry. Go ahead, Sarah.
just to build in there. So if the robot, you had the overtrust inertia,
Mm-hmm.
the robot or system makes some mistakes, will that inertia also start to go the other way?
So a lot has to do with the timing of the mistake. We definitely see some Gestalt effects. We actually did a study where we manipulated the timing of when a robot failed during a urban search and rescue simulated experience, and that does the timing really does matter. It's really important for a robot system to show that it can do its job in the beginning. And humans will tolerate some mistakes, but if they don't see that it can do the job and do it well in the beginning, you're gonna have some trouble.
Thank you.
Okay, Aaron, if you're willing to answer one last question,
Sure.
we're about out of time, but maybe briefly, if you can talk a little bit about your thoughts on using robots and AI to combat social isolation.
Yeah. So there's been some really cool work in this area. There's a robot called Paro, P-A-R-O. It looks like a seal, like a little furry seal. And they've had some really, really promising results from testing. Multiple groups have tested this, and there's been multiple studies that show some really fascinating results with this. And there's been other people attempting to do this as well. To be blunt, we have a number of countries that are having increasing aging societies. There's going to be a shortage of healthcare workers and caregivers. I think that these sorts of technologies are going to be really important for maintaining morale. I also think some of these AI systems can be very powerful in terms of maintaining skill and maintaining cognitive sharpness. It's a lot better for a person to be interacting with a conversational system than watching TV all day, in my opinion. That's just, I'm not a gerontologist, but from what I've heard and seen, it's important to stay mentally active and engaged. And I think that these sorts of systems do have this potential. If you haven't seen it, there's a wonderful movie called Robot and Frank that really digs into this from a fictional perspective. But a lot of people in the field are kind of like, this is a great movie. The other thing that I think is going to be really important for engagement is there are certain things you can do with AI that supplement and buttress human-human interactions. And an example is automatically generated captioning. All of us have had that family member who you call them up on the phone and it's really clear to you they don't understand what you're saying, right? But if you give them a caption telephone, you might have a much better experience and a much better engagement. Caption telephones, to do that at low cost and high volume, more and more captioning is useful, right? Essentially, and to do that well, you need to have really good speech systems, and that means you have to have good AI systems.
Okay, so I think that wraps up our webinar for today. Thank you again, Aaron, for this really fantastic talk.
Glad to be here.
Thank you for all of our attendees. And great questions and great discussion. Yeah. So
and one of these days I'll have the opportunity to see you all in person somewhere.
Yeah.
We appreciate that.
Hopefully we can work together.
Great. So we will make this video as well available. So
Yep.
if you'd like to share that, we will also send that video link to all the attendees. So thank you, everyone, and have a good day. Take care.
Thank you.
Bye.
Bye.